All right, so now we're going to do a conceptual overview of binary search trees. We're not going to really get into the coding of it today. We're going to just talk about it from a conceptual high-level perspective, and we'll get more into the programming of it next time. So to introduce binary search trees to you, I'm going to give you guys a puzzle from a D&D game that I wrote and published back in 2000. Debuted at San Diego Comic-Con and has since been rewritten by one of my colleagues who's a school psychologist at our college of all things, but JJ10, who's a great guy. He's in, I think, Wisconsin now. So this puzzle, you find yourself in a dungeon and you need to escape. So we got some dungeon music going on there, MIDI dungeon music from Daggerfall, the best Elder Scrolls game there is. And so you're in this dungeon, and the Mines of Moria, whatever. It's not actually the Mines of Moria in the game, but it's trademarked by Tolkien Estate. But you're in some sort of dungeon, okay? Some nice trademark-free, copyright-free dungeon, all right? So, yeah, there you go. All right, so Marsh, you're up first. You're in a dungeon, and in Dwarvish it says you must find the EXIT, all right? And in front of you are two doors. One of the doors says in, and the other door says in. Do you take the left door, or do you take the right door? Chicken Marsh. Which one do you take? The M door, all right? Behind the M door is the letter G written on the ground. Do you take the left door, or do you take the right? Choose wisely. If you take more than 5 seconds, you know. The left door? Alright. On the ground is the letter D. Do you take the left door, or do you take the right door? Right door? Alright. On the ground is the letter F. Do you take the left door or the right door as you're winding your way through these things? Left it is. Very good. First time. You find the letter E and a small button. You push it, and the first of the doors, of the bars on the door, open. Okay, so Jose Santiago, you're up next. Do you take the left door or do you take the right door? The north door? Oh, and the end door. Yeah. Good. On the floor is the letter T. Do you go left or do you go right? R? Oh, right. Okay. All right. Congratulations. You also make it. Bean. Which way do you go? Right is always right. Which way do you go? You die. Okay. Everyone else, you see Bean's smoldering corpse on the floor in front of you. Who wants to go next after that exciting thing? We've got 2 people that made it and 1 person who died. In the noon class, I killed 90% of the students in the class. All right, Sartorelli, is F your choice, or is that you're paying respects to the dead students in the noon section? Paying respects. All right, you're up next then. So do you go left or do you go right? All right, let's do this. Left. That seems like a good option considering right killed Mr. Bean there. On the floor is the letter G. Left or right? Left again. You die. All right. Who wants to go next? All right, Wallace, you go left. There's the letter G. Which way do you go? Right. On the ground is the letter J. Which way do you go? You die. Ah, so close. Okay, Burford, you're up. So this one is like after 2 flawless traversals of the dungeon, we're now stacking the body count up. All right, Burford goes to the left. Seems like a good idea. Floor is letter G. Which way do you go? Right. Okay. You see Wallace's corpse to the right. So left. So you guys are just brute forcing the dungeon. Congratulations, I guess. Like you literally hit every trap on the way to that one. All right. So Burford, go again. Which way do you go on this one? Right. Congratulations. All right. So, for those of you that didn't understand, this is alphabetized, right? So the letter T is to the right of N, right? The letter I is to the left of M, right? So it's just alphabetized. That's it. Nothing fancy. Although one of the times when I was running this at Comic-Con, a guy was like, "This is a binary tree." I'm like, "Yeah, so what? You know, it's just alphabetization. Like, there's nothing to do with computer science in this." It's like, you can't put a binary tree in a D&D game. I'm like, I don't know. I just did. I just did. So yeah, all right. So basically, this is kind of a conceptual overview of binary trees. Binary trees aren't one-dimensional. All the other data structures, M is E if you shift it. Yeah, you rotate the M to the left or something. No, that's just alphabetized. That's it. A's to the left, Z's to the right. All right. I hope you paid attention, Gunner. I'm using this in my next D&D game. Yeah, the deaths were all illusionary, but it would deal, the traps would deal 20d20 damage, and I remember one guy getting really upset at me that a trap would do 20d20 damage to an 8th level character. He's like, that's not fair. That's not fair. I'm like, it's a trap. Who cares? You know. So yeah, Marsh getting it right on the first try is very good. Okay, so vectors are kind of definitionally a one-dimensional vector. A linked list is one-dimensional. An array is one-dimensional. A binary tree, though, kind of branches. Every tree has got 2 subtrees. Looks very similar to a linked list if you look at the source code for it. Let's see, like this. So the source code for a node on a binary tree looks very similar to a doubly linked list, right? You got a previous pointer and a next pointer and a data. Hey, look, you understand what templates are now. With a binary tree, you've got a left pointer and a right pointer and a data. So it's very close, actually, to just a doubly linked list, except the way that it's laid out looks like this. So let's go through some terminology. So in computer science, a tree has its root in the air. I don't know who thought this is how trees look like, but trees apparently grow like this in the imaginations of the computer science majors who have never seen trees in their life. These are called the leaves down here. So the leaves are on the bottom of the tree, and the root is in the sky. Yeah, if you ever needed better evidence that computer science majors need to touch grass, there you go. They're like, what is a tree? Which way is up? I don't know. I've never seen one. Okay, let's put the root in the sky then. All right. Yeah, that's all I got for you. I don't go hiking, Dykstra, whatever. Okay, so this is the starting point, okay? The only trees you see are the branches from outside the window. Yeah, it's probably like, I don't know which way the root is. I'm just going to guess up. Okay. So the root is kind of like the head, right? Like when you had a linked list, you'd have like a head pointer pointing at the head of the linked list. The root is kind of like the beginning of the tree. That's where you enter the tree. That's where you begin every time, basically. Yep. And every node has 0, 1, or 2 children. Okay. So the root has 2 children. These 2 guys here and here. A here has got a parent up there. It's got 1 child there, 1 child there. Okay. And this guy's got a child here and a child here. Assuming that's actually a child and not like a null pointer or something. Okay. And then the very bottom level are leaves. And so here we have leaves here, 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 and here. A leaf means that it has no children. Okay. Which I guess is technically true of a tree. Maybe? I don't know. Does a leaf mean it has no children? Okay. So here's what it looks like using actual numbers. All right. So here's the rule for binary trees. Here's the rule. Everybody to my left is smaller than me. Everybody to my right is bigger than me. This is a recursive property. Every node of a binary search tree is a binary search tree. And so that's the invariant. Remember how we've been talking about invariance and hammering class invariance this whole semester? There is an invariant for a binary tree that every element left of me, in other words, within the left subtree, is smaller than me. Everybody in the right subtree is bigger than me. If there's nobody in the tree, it points to null. That's about it. Okay. For the invariance. So let's do a insert. So let's say we're going to insert the number 30. Okay. Let's say we want to insert the number 30. All right. So Wallace, you still here? All right. You got to go first. Does 30 go to the left? Does it go down to the left? Or does it go down to the right? Which way do we go? Right. Okay. So we're here. Do we go down to the left or do we go down to the right? Left. Go down to the left, go down to the right. Perfect. Round of applause for Mr. Wallace, everyone. Yeah, so we're going to have a new person inserted right there. Because 30 is bigger than 27, you go to the right. Oh, it's smaller than 58, you go to the left. It's bigger than 28, go to the right again. You guys see how that works? So the dashed lines, the dashed boxes here are, like null pointers, right? Essentially. Okay, so what about if we wanted to insert, so it'd be on the left half of 20. Okay, Viala, you're up next then. What about 19? Go ahead and insert 19 into this tree. We're doing 19. Is 19 smaller than 27 or is it bigger than 27? If it's smaller, we recurse down to the left. If it's bigger, we recurse down to the right. Could you go inside any box? Well, there's only one box that it can go into. Does that make sense? There's only one correct answer for which box it goes into. And that box is the one where it is, bigger than, what I mean? It's got to be smaller than those people and bigger than these people. Okay. 28. Okay. Gotcha. So, all right. Anyhow, it doesn't matter. You've been Volin chosen. So, which way is 19 going to go, Kevin? We're here at root. Do we go left or do we go right? Left. Okay, cool. We're here. 19. Left or right? Got a nice open spot right here. Doesn't that look? No. Okay, couldn't fool you. Good. Left or right? Right. Cool. Left or right? 19 is bigger than 17, and we finally found a null pointer. So we'll just new a little node here and connect it up and make a couple new null pointers over here. And that's it. And so that's how a tree grows. Now your question was, what happens if you insert 27 or any duplicate? The rule for a binary tree in general is you discard the duplicate. Because binary trees kind of represent a set. And either something is in the set or not in the set. So if 27 is in the set and you try adding it again, then, nothing happens. Okay. So you have to check to see if your value matches the new guy you're inserting. If it matches it, then smaller amount to the left, bigger amount to the right is exactly it. That's it. And if it's the same value, stop. Okay. So like if you were inserting 65, you'd if you were inserting 65, you'd go to the right, you go to the right, you're like, oh, look, that's a duplicate, and then you just return without doing anything. So that's insert. All right. Let's do search. Okay. So search. Stevie, let's search for the number 85. So let's search for 85. We're going to return true or false. Is it in the tree or not? Okay. So we started the root. Right? Which way do we go? Stevie, right here. Is 85 bigger or smaller than 27? We go to the right. All right. Which way do we go now? It's just like the dungeon delve puzzle. Go to the right again. All right. Oops. Ah. Okay. Which way? Is 85 bigger or smaller than 65? Go to the right again. Good. Let's see if I can circle it properly this time. There we go. All right. Is 85 bigger or smaller than 74? Go to the right again. Is 85 bigger or smaller than 82? Go to the right again. Is 85 bigger or smaller than 92? Go to the left, and we hit null pointer. So what do we return? True or false? True, we found it. Or false, we did not find 85 in the tree. What do you think? False. Mm-hmm. Yeah. So 85 is not in the tree. All right. And the cool thing about this is if your tree is balanced, then let's see here. Okay. If your tree is balanced, like how many do we got here? We got like 32 nodes, 31 nodes, something like that. Here. What is the maximum number of iterations we need to do in order to return true or false is 80 in this binary tree here. Like imagine each one of these things has a number, like that's 50, and that's 70, 75, and that's 100, you know what I mean? So imagine each one of these nodes has a number on it. What is the maximum number of repetitions we need to do until we can return true, that number is in the tree, or false, that number is not in the tree? There is not a sort function for binary trees. Binary trees are always sorted. So binary trees are order 0 sort, which is something of a meme, but it's also kind of true. You can't sort a binary tree. They're always sorted. So it takes zero steps to sort a binary tree because they're literally always held in sorted order. Smallest guy is going to be this one, right over here. That's always going to be the smallest element in the tree. This one's the biggest element in the tree. Always. You don't have to do anything to sort it. It's always sorted. Okay. So how many possible searches would it take for us to find any element in this tree? 1, 2, 3, 4, 5. Or 6 if you're counting the null point over here. Whatever. So if you have 32 elements, you could just go, like if you had a vector and you wanted to go through all 32 elements in the vector to see if the number is in there or whatever. Yeah, that's an order n search. With a binary tree, though, when you have a balanced binary search tree, I call these things binary trees, but they're really binary search trees. Because a binary search tree means it's got that property, everybody to my left is smaller than me, everybody to my right is bigger than me. You can have a binary tree that's not a binary search tree. We'll learn heaps, for example, later on. So if you have a balanced binary search tree, then you are talking about an order log n insert, search, and delete. If, however, you have an unbalanced VST. I'll show you what that looks like in a second. Then you have order N. Insert, search, and delete. So what's the difference between order N and order... Yeah, you're good, Walls. What's the difference between order N and order logN? If you have 1,000,000 elements. How much faster is a balanced binary search tree at searching, inserting, and deleting than a vector? Right? Let's say a vector at searching. Let's say, but it doesn't really matter. Like if you have a vector and you want to like search for the number 42 and delete it, that's order N. Because you have to find it, which is order N, then you delete it, and that's order N. Works out to order N. But a binary tree can do it in logN time. How much faster is the binary tree than the vector at doing that delete versus the vector? Anyone know? Because we don't really think about logarithms that much in our daily life. They're kind of a weird, obscure part of algebra. But Luke Olson has it correct. It is 50,000 times faster. logN is not just fast, it is blazingly fast. It is as fast as how slow exponential is. Okay? So it's not as good as order 1. Hash tables can do order 1, insert, search, delete. But it's pretty good. And in all fairness, it's really fast enough for almost any purpose. When you have a key in a database, what it does is it generates a binary tree, a balanced binary tree, for that column. So, for example, if you're at the DMV and they have a key, like they're like looking you up in the system. If they have a key for the social security number, let's say, then that means they've built a binary tree for all 100 million people in the DMV database. And so if there's 100 million people in the DMV database, how many steps does it take for them to find your social security number? How many operations does it take, roughly? We don't care about fiddly things like plus or minus 1 here. If you have 100 million people in the DMV database, if you have a key for that thing that you're searching for, how many operations roughly does it take? It will take, good, log base 2, will take 26, 27, thereabouts, operations, worst case. Okay. So would you rather do 100 million operations if you're the DMV? Would you rather go through every person in the California database one at a time and see if they match? Or would you rather take 27 steps? Now think carefully. This is a trick question. 27, the DMV doesn't need to be any slower. The movie Zootopia has a scene where it's sloths processing the DMV. So yeah, no joke. Like the last time they had to look me up in the system, it took like 5 minutes. And the only reason that I can think of, other than just extreme incompetence, is that whoever it was that designed their database didn't add a key for like last name or something like that. And so instead of finding my name in 27 steps, it took 100 million operations to go through every person in California looking for somebody whose last name was Crane. Okay. And I sat there for I was like baffled and confused. I'm sitting there for 5 minutes just staring at the computer like, why has it not found me yet? And they're just like, it's just this slow all the time. And I'm like, why? Like, as a computer science major, as a computer science professor, I'm like professionally like upset. It's like, if you're a doctor, and you see somebody like with bad stitches or something, you're just like, I'm just professionally offended, that somebody stitched you up that badly. They didn't believe you were real. Yeah. 5 minutes to find me. Yeah. And now, to be fair, every time you add a new key on a column, it has to generate a binary tree for all 100 million people, right? And that takes up a fair amount of RAM, right? If you're doing it on literally everything. So if you can find somebody based on their middle name or something, like, you're going to have to hold that binary tree of all 100 million people in RAM somewhere, or more complex, page parts fit out to disk or whatever. But yeah. Okay, so let's see what a non-balanced, an unbalanced, an imbalanced tree looks like on the left. And on the right-hand side, we have a balanced tree. Okay. So do you guys see why search and insert and delete on a non-balanced tree, an unbalanced tree, is order n? So if you want to insert 10, right? It's got to go to the right, 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 go to the right. And they use those rinky-dink computers. Yeah, I think they're connected to a mainframe or something. And who knows? Maybe the mainframe was just being hammered, but it doesn't take that long to do 27 operations. You know what I'm saying? So 5 minutes is an awfully long time. Okay. So remember, if you have an unbalanced BSD, it's order n, insert, search, delete. You guys see why? So if you insert 10, you have to go to the right, go to the right, go to the right, go to the right, go to the right. So you're literally going through every element in the tree to insert it, or to search it, or to delete it. Okay. We are not going to cover in this class how to write a balanced binary search tree. Okay. That is probably, you're probably going to see this as a junior. Red-black trees, AVL trees, things like that, are self-balancing trees. That's a classic junior level data structure assignment, right? Write a red-black tree, right? I used to I TA'd that class, and I could write red-black trees in my sleep, basically. But not in this class. We're not going to give you anything more complicated than just a tree that might be unbalanced if it happens. You guys think of what sort of inserts, what sort of data would cause you to get an unbalanced tree like this? Insert what, insert what, insert what, insert what. What sort of data, if you insert it into our naive tree there that just finds a spot and puts it in, what sort of data will cause it to become unbalanced like this? What is the worst case scenario for our data with our basic binary search tree here? Insert sequentially increasing integer values. Yeah, well, they don't have to be sequentially increasing. They could just be monotonically increasing, right? Scientific numbers, yeah. Basically, just sorted, any sort of sorted data, which is usually how you get data, right? When you import data from a data set, it usually comes in sorted. And so if you take all that sorted data and then put it into a binary tree, you will get the tree on the left. And you will be really wondering why your binary tree is so slow when you guys are doing the benchmarking on this. Why are my tests, why are my benchmarks taking 5 hours to run instead of 5 seconds, right? Why is it so slow? So one thing that you could do is you could shuffle the data and then insert it. that'll probably be good enough, Just shuffle it and then insert it. Because it's very common for you to get sorted data. And sorted data is death for a binary tree like this. So yeah, just take the deck of cards, throw them in the air, gather them up randomly, and then feed them in, and you'll probably be fine. You guys understand the difference between balanced and unbalanced? Worst case scenario, if you're deleting 6, you have to go all the way down to the end. Boom, 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 boom. With a balance, you only have to go down logN times. Okay. You guys understand? Balance, unbalanced. Yeah. So if we're inserting 11, go to the right, go to the right, go to the left. Hey, there's an open spot. Insert. And that's it for today. We're just doing a very simple conceptual overview of binary trees. Deleting is a little bit hard. We'll have probably a complete lecture just on deleting from a binary tree because it's kind of a pain. There's you got cases where you're deleting somebody with no kids, 1 kid, 2 kids, and then deleting root if you're the last So you have to like special case like 4 different scenarios, and it's not hard, but it's kind of annoying. So your questions for today are conceptual. Here's a binary tree. If you insert 52, what slot does it go into? So if you guys could follow that, you're good. You're good for the quiz for today. Deleting from a linked list. Yeah, it's harder though, because like if you delete from the middle, yeah, but like with a linked list, you have deleting from the head, deleting from the tail, deleting from the middle, and deleting the last element. So those are 4 different special cases, but it's actually harder because if you have 2 kids, you can't just delete it and replace it with the 2 kids because now your parent has 3 kids. So there's a trick to it that we'll go over. Huffman codes of a balanced tree is always 1. Huffman code of a balanced tree is always 1. I'm not following you. So Huffman codes will generate a balanced tree if you have all the same frequency of the letters. That's what you're talking about. Okay. Yeah. So that's it. That's just concept for today. And we will pick this up again on Wednesday. Peace out. See ya.